In this lecture, we're going to talk about linear dependence proofs. First, let's talk about the technique for completing these proofs. The first step is to take the proof and start with an assumption and translate that assumption into a mathematical statement. And generally, you use precise mathematical definitions to do this. In the second step, we identify what needs to be shown or proven, and again, using definitions, we translate that into a mathematical statement. In the last part, we just try to manipulate the statement that we receive in step 1 to get the one that we need to prove in step 2. So let's consider the following theorem that deals with the linear dependence of two vectors. So the theorem says the following: a set of two vectors is linearly dependent if and only if one of the vectors is a scalar multiple of the other. Now this theorem has an if and only if statement, which we see here. That if and only if means that we can read this statement in two ways. The first way is the following: if a set of two vectors is linearly dependent, one of the vectors in the set is a scalar multiple of the other. All right, so we start with the assumption here that the vectors are linearly dependent, and then we must prove that one is therefore a scalar multiple of the other. The second statement is that we start with the assumption that the set of vectors, in the set of vectors, one can be written as a scalar multiple of the other, and then we have to show that the set is therefore linearly dependent. So to complete the proof, we actually have to prove both statement 1 and statement 2. We're going to start by proving statement 1, and we're going to employ the technique that we had previously to prove it. So it says, if a set of two vectors is linearly dependent, one of the vectors in the set is a scalar multiple of the other. So from step 1, we want to start with some assumption and translate that assumption into a mathematical statement. Notice that this theorem starts with the statement, if a set of vectors is linearly dependent. So that is what I'm going to start with as my assumption. I'm going to assume that I have a set of two vectors given by S that is linearly dependent. Now I must translate this statement into some type of mathematical statement using a definition. Well, notice here that we say the set is linearly dependent, and we have a mathematical definition for that. So let's employ that now. So the definition of linearly dependent tells us that if I take this set of vectors and put them in linear combination, that in the homogeneous equation, that homogeneous equation has non-trivial solutions. And what it means for this linear system to have non-trivial solutions is that x1 and x2 are not both zeros. Right, so at least one of these is a non-zero value. So let's move on to the next step of the proof. It says identify what needs to be proven and translate it into a mathematical statement. What needs to be proven is shown in the second part of the statement, which is one of the vectors in the set is a scalar multiple of the other. If we translate this into a mathematical statement, then what we really need to show is that one of the vectors, let's say v1, is some scalar multiple of the other vector v2. We could have chosen v2, but it doesn't matter which one, so we'll choose v1. So in this third step of our proof, we need to now manipulate this mathematical statement that we generated in step 1 and obtain the one in step 2. So here you see that we have from the first statement that the homogeneous equation has non-trivial solutions, and what we would like to get to is that v1 is some scalar k times v2. From our first statement, we assumed that the homogeneous equation had non-trivial solutions, which means that both x1 and x2 are not simultaneously 0. So let's assume that x1 is a non-zero value, right? So we get that right there. Now remember, my goal is to get to the statement that v1 is some scalar multiple of v2. So what I'm going to do now is take this homogeneous equation and subtract x2, v2 from both sides of the equation. If I do that, I get the following. I get x1, v1 is equal to minus x2, v2. Now I can divide by x1 on both sides of the equation, which gives me that v1 is minus x2 over x1 times v2. Now you can see why it was important for us to say that x1 was non-zero, because if x1 is equal to 0, then I'm unable to divide by it. Right, so actually we're finished, because notice that I can let k be the quantity minus x2 over x1, which then gives us that v1 is k times v2. Right, so in this case, our proof is complete. We've now completed the proof of statement 1, but remember we said that the theorem would not be complete until we proved both statements. So I would like for us to look at statement 2. It says, if one vector in a set containing two vectors is a scalar multiple of the other, the set is linearly dependent. I would like for you to now pause the slides and actually go about implementing the steps of our technique to see if you can prove this statement. We are now going to look at different sets of two vectors and try to determine, based on our theorem, whether or not the sets are linearly dependent or linearly independent. So let's look at the first example. Here we have the vector v1, which is 1, 2, 0, and v2, which is 3, 6, 0. Notice that, in this case, v1 is 3 times v2. Well, what does this mean? Let's take this and write it as a homogeneous linear system. So I'm going to subtract 3v2 from both sides of the equation. So notice I've taken the set of vectors, and from it I have generated the homogeneous linear system that looks like this. And also notice that the weights, in this case an implied 1 in front of v1 and negative 3 in front of v2, are non-zero. So this tells us that this linear system has non-trivial solutions. Hence we can conclude, based on our theorem, that this set is linearly dependent. Now let's look at the second set. Here we have v1 and v2. v1 is 1, 0 and v2 is 0, 1. Notice that there is no way that we can write these two vectors in linear combination and get the 0 vector without x1 and x2 being 0. But all we really need to see is that v1 is not a scalar multiple of v2. So we know that v1 is not some scalar quantity times v2. So automatically we can conclude, based on that, that this is a linearly independent set of vectors. We are now going to prove what is known as the linear dependence theorem, and this deals with the linear dependence of two or more vectors. So the theorem states the following: a set of vectors, v1 to vp, is linearly dependent if and only if at least one vector in the set can be written as a linear combination of the others. So again, as in the previous case, there are two statements that need to be proven. The first one is, if a set of two or more vectors is linearly dependent, one of the vectors in the set can be written as a linear combination of the others. And the second statement is, if one vector in a set containing two or more vectors can be written as a linear combination of the others, then the set is linearly dependent. So we will start by proving the first statement. So I'm not going to write down the steps that we used to to prove the statement. So what I'm going to do actually is just go through the process, and you'll see the steps as the proof evolves. In the first statement, what we are given is that we have a set of two or more vectors that is linearly dependent. So what that gives us is that if we look at the homogeneous equation with those vectors in it, that homogeneous linear system has non-trivial solutions. What we would like to show is that one of the vectors in the set can be written as a linear combination of the other vectors in the set. All right, so we can write that in the following way. Show that, let's say, the jth one, so I just chose an arbitrary vector out of the set, it doesn't matter which one I choose, can be written as a linear combination of the other vectors in the set. So again, we have our homogeneous linear system, which is written here, and we know that it has non-trivial solutions. Because of that, we know that not all of these x's, that is the coefficients in front of the unknowns, or the vectors, are going to be zeros. So let's say that we order them so that the first j vectors have non-zero x's. Then our homogeneous linear system would look like this. Notice the ones after the jth one, and I'm actually missing the jth one, so please insert the following. You want to put in xj, vj. Right, so all of those after the jth one have zero coefficients. Since the vectors vj plus 1 to vp all have zero coefficients, then I can eliminate them from my linear system, and I end up with an equivalent system, but in this case, all of these x values are non-zeros. Remember that my goal is to get the jth vector written as a linear combination of the other vectors in the set. So what I'm going to do is I'm going to take all of these vectors on the left-hand side, other than the jth one, and subtract them from both sides of the equation. If I do that, I get the following. xj vj is equal to minus x1 v1 minus x2 v2 all the way up to xj minus 1 vj minus 1. Now all I need to do is divide by the value xj on both sides, because of course we know that xj is a non-zero element, and that's what we needed. So we have vj is equal to minus x1 over xj v1 minus x2 over xj v2 all the way up to xj minus 1 over xj vj minus 1. At this point, we're really finished with our proof, because we can simply let these values be scalars. Let's make the x1 over xj c1, and let's let c2 be minus x2 over xj, etc. So you see now that vj is just c1 v1 plus c2 v2 all the way up to cj minus 1 vj minus 1. But guess what? The other vectors are also in there. Remember, these go all the way up to vp. It just turns out that the rest of those coefficients, the c's in other words, are simply zeros. So we do have all of the vectors up to vp. Hence we have shown that vj, which is one of the vectors in the set, can be written as a linear combination of the other vectors. The second statement says that if there's a vector in the set that can be written as a linear combination of the others, then the set is linearly dependent. So notice what is given is that one vector can be written as a linear combination of the other vectors. So that is the part that we see here. And what we need to show is that the set is linearly dependent. Hence, we need to show what you see underlined in red, and that is that the homogeneous linear system has non-trivial solutions. So starting with the equation that's outlined in blue, let's now just take the jth vector and subtract it from both sides. So you'll see that that vector now shows up on the other side of the equation in its rightful place. So to the right of that would be the vector xj plus 1, vj plus 1. We've just left it out and it's included in the dots that we see there. So if you look at this, now we've taken, in other words, the one in blue, and we've rewritten it as a homogeneous equation. Notice that the weight on Vj, which here is an implied -1, is non-zero, which automatically means that all of the coefficients are not zeros. So we can say that that homogeneous linear system has non-trivial solutions. So we're really done, right? All we needed to show was that the homogeneous linear system had non-zero solutions, or had non-trivial solutions. We can therefore conclude by the definition of linear dependence that the set S is linearly dependent.